Hello and welcome to this session where we'll take a look at the concrete beam module within Structural Engineering Library. The first thing that we'll do is see how we can add a concrete beam module to an existing project file. So I'll click on Calculations in this project file, and then I'll click the Add button, and then I'll come down to the Beam category and choose the option to add a concrete beam. Now my screen reconfigures to show us the concrete beam module, and we'll just take a walk through what we see in the graphical user interface here at a fairly basic level to begin with, and then dive into each of these areas in more detail. So starting at the top of the screen, we have a graphical input area where we see a representation of a concrete beam, and we'll use these tools to set the support conditions, the number of spans in the model, the span lengths, and so on. Related to that graphical area is the next area below, which is generally what I think of as the data input panel. It consists of a series of tabs that are oriented horizontally, and through the video we'll actually touch on each of these tabs in detail and understand all of what we see in each of those tabs. But in general, at this stage, just understand that this panel is the location where we'll interact with the program to provide it with numerical input and provide it with all the values that we need to establish and define the physical model, the design parameters, the loading, the load combinations, material strengths, and so on and so forth. This next panel below is what I think of as the results or output panel. It also has some subcategories to it, starting with a vertically oriented set of tabs on the left. And then for the calculations tab that's currently selected, we can even see that there are some horizontally oriented sub-tabs. And again, we'll take a thorough walk through all of the options that appear down here in the results panel. But for now, just understand that this is the location where you'll come to see the design status for your beam and all kinds of important output results, such as reactions or shears and moments, diagrams, maximum and minimum values, and so on. The last thing that I'd like to point out as we tour the graphical user interface of the concrete beam module is this small strip down at the bottom that I refer to as the status bar. Right now it just indicates recalc complete on the left, and it shows that I'm creating the video in build 6.12.9.26 over here on the right. The status bar is important throughout the modeling process because that's the location where the program will communicate with us if we have an issue of some sort that needs to be addressed. And specific to the concrete beam module, some of those things that it may be telling us are that we have a span that has no reinforcing defined for a certain segment of that span. Or it may indicate that we have an issue with a reinforcing ratio, either that we have not provided enough reinforcing or that we've exceeded a maximum amount of reinforcing that's permitted. So there are a variety of messages that we can pick up from that status bar, and it's important to make sure that it's in view as you work and that you glance down there every so often to make sure that the program isn't trying to communicate something important to you. Okay, with that basic introduction, the next thing that we'll do is move back up here to the beam graphic, and we'll start to discuss how we can assemble or develop the physical model of the beam that we want to analyze and design. One comment that I'd like to make before we actually start to construct our physical beam model is that the structural engineering library is set up so that it automatically recalculates with every change that's made to the model or to the input data. And this is very convenient when you're at the stage of fine-tuning a design and you like to see the effect on the results very quickly. However, when you're at the stage that we are at, where we're just beginning the modeling process and we're going to be making wholesale changes to the span, the number of spans, support conditions, and so on, recalculating after every one of those steps starts to become a little bit wasteful because we really don't care to see results at this stage of the game, so it doesn't make a lot of sense for us to wait for the program to process all of the different load combinations and potentially even multiple permutations of unbalanced live load. So with that in mind, I'm just going to reach down here to the auto calculate option, and I'm going to deselect that right now, which spawns off the calculate button, which is the way that we can force the module to manually recalculate on demand. But that will suppress the automatic recalculation after every single change. So now I can be a little bit freer to make some changes a little bit quicker and not worry about having to wait for those recalculated results. Now what I have in mind for our sample beam here is to create a 2-span condition where I have a 20-foot span on the left and a 10-foot span on the right. So what I'll do is I'll come over and just point out that there's a message here beneath the graphical input panel that says click on the plus and minus buttons to add or delete spans. This is one of those plus or minus buttons that would add a span or delete a span on the left side, and here's the one that would add or delete on the right side. And then notice also that there's a note down here that says click on the supports to modify. So if I hover over either of the supports in the current model, it comes up as a little icon and indicates that it's currently a pinned condition. But notice if I click on that support that I get a drop-down menu that offers different options for support conditions at that location. So that is the way that you can change the support conditions at any location where a support is defined. And then the next thing I'd point out is this note in the center that says click on span to select. Now right now we only have a single span beam in our model, so it's selected by default, but that's a perfect segue into adding that second span that we talked about so that we can see what it looks like to select a span. So I'll come over to the plus and minus icon on the left hand side and click that, and we get the select, add, or delete dialog. This gives me the option to add a beam, and it also down below gives me some options for treatment of that new span. We can either choose to use the current span length and bracing values or not. We can choose to use the current beam size and properties or not, and then we can also choose whether or not to use the current loads, if any have been defined on the span that already exists. So I'll just leave those set as check marks for now, because we're going to come back in and revisit all of those individually anyway, so it really doesn't matter for the purposes of our exercise. But I'll just click OK, and now we can see that we have a 2-span beam, and now it's a little easier to see that the left span is the yellow, which indicates that it's selected, and if I came over and clicked on the right hand side, it becomes the yellow or the selected span. And we'll see the importance of selecting a particular span in the next step, which is to set the span length. Now this is the only thing about constructing the physical model that we can't actually do up here in this little topmost pane, but instead what we'll do is just jump down to the beam span data tab, because that's the tab that we use to establish the span lengths for the 2 spans, or for however many spans are defined in the current model. Now we can see that span number 1 is selected because span number 1 button is depressed, and also that if we click on the number 2 button, that switches to select the number 2 span. So these buttons correspond to the yellow highlights seen up here in the graphic. What I'd like to do is I'd like to just set this left hand span to 20 feet. So while the number 1 is clicked or the left hand span is selected, I'm going to just overwrite the value of 10 with a value of 20, and then click in another field so that it registers that data, and there we can see that we've established a 20-foot span. Now by way of example, if we wanted to come in and, for instance, make the right hand end of this 10-foot span unsupported or a cantilever, then what we could do is click on that support and choose the free end option, and notice that now the graphic changes to represent a free end. That's not actually what we intend to do for our example, just wanted to point out that that's how that can be used, so I'll just reset that to a pinned support. So at this stage of the game, and I'll toggle back to the general data tab, We've used the panel in the uppermost portion of the screen to set up the physical model for the beam that we'd like to create. And the next step will be to go through these tabs in the data input panel in order, generally from left to right. And so we'll do that and visit each of those tabs and talk about all of the options that are available there. The first thing that we see on the General Data tab is the description, which is just a general input field where we can enter anything that's meaningful to us. So we might put in a description like beam B1, for instance. The next category is called beam material, and we can see that because we added a concrete beam calculation, the material is indicated to be concrete. If for some reason during the design process we decided that we wanted to change the beam that we had configured from concrete to, say, a steel beam, we can actually toggle to a different material, which would spawn off a different calculation module and carry over as much of the data as it could into that other module. Our intent with this video is to focus entirely on the concrete beam module, so we'll keep the material set to concrete. The next category down is called support type, and here we have two options. We can choose the option which allows us to configure a conventionally supported multi-span beam like we're working with here, or we can choose the option to define a beam on an elastic foundation. If we went with the beam on elastic foundation option, what that would do is provide us with an input for the length of the beam, which would be a single span by default, and it would also allow us to input a subgrade modulus of reaction that would be used to multiply by the beam width to come up with the stiffness of unit springs that are modeled all along the length of the underside of the beam as compression-only springs. Now if we move over to the right-hand side of the General Data tab, we can see a category named Design Values. This is where we'll provide all the information for material properties such as the compressive strength of concrete, the modulus of rupture of concrete, the unit weight of the concrete. If it happens to be lightweight concrete, we can specify the lambda factor. This is the input field that we'd use to specify Young's modulus for the concrete, and notice that there are two convenience buttons that provide values quickly based on two commonly used formulas for Young's modulus of concrete. Continuing down, we collect the phi value that we want the program to apply for flexure and the phi value that we want to apply for shear. Moving over to the upper right, we collect the yield strength for the main rebar and Young's modulus for the main rebar, and then we separately allow you to specify the yield strength and Young's modulus for stirrups. And then we collect the stirrup bar size and the number of resisting legs per stirrup, and we report the value beta 1. The last thing that we collect on the General Data tab is the maximum allowable live load deflection ratio and the maximum allowable total deflection ratio for use in comparing and reporting on deflections. So our next step will be to move over to the Beam Span Data tab. Now we've already seen the Beam Span Data tab in use in order to set the span length for our left span. But now we'll take a look at all of the other options that are available for us on the Beam Span Data tab. In addition to the span selector, so that we can choose the span that we're currently discussing or describing with these controls, we also have the span length spinner, so we can adjust span lengths. We can set the total height, but I would point out that this is not span specific, so if I bump this up to say 20 inches deep and then toggle over to the other span, notice that it too is 20 inches deep. So we don't have the ability to define sections differently on a span by span basis. So just keep that in mind when working with both the total height and when working with the width input spinner. The next category over is the beam shape. So we have the option to specify rectangular shapes or H-shaped or I-shaped sections, trapezoidal shapes, L-shaped sections, and inverted T's. And for each of those different sections, you'd see a slightly different collection of geometric information that's required over here on the left side to accurately define that shape. For our purposes, we'll just stick to the simple rectangular section. Moving over to the right, we can see a graphical representation of the currently selected span. So in this case, span number 2, the right-hand span is the one that's selected, so that's the one that we're seeing. I'm going to toggle back over to span number 1 and think my way from left to right on this beam. What we're going to use this diagram and these controls for is to define the rebar that exists in each of the spans. And what I'd like to do now is I'd like to show how rebar can be defined both full length of the span as well as rebar that could only run partial length of the span. Now we can see that we have a bar set that's coded with this blue color already defined by default, and it currently shows 2 number 6 bars that are located at a distance of 3 inches from the bottom of the span, and the position of the bar runs from 0, or the starting end of the span, to 20 feet, which is in this case the full length, the overall length of that span. So what I might do here is just bump this up, and let's say that we want to use 4 number 6 bars, and instead of being located 3 inches from the bottom, let's leave these 2 inches from the bottom, but still let them run full length of the span. Now because I have a 2-span continuous beam here, I'm going to load it in such a way that we'll develop some negative moment at this support, so we'll have tension on the top, so we'll definitely need some rebar in the top of this beam. So what I'd like to do is use the spinner arrow on this bar set number 2, which will be color coded in green, and I'm going to run this up to 5 number 6 bars, and I'm going to use them at the top. So I'll select the top option, and then I'm going to move them so that they're 2 inches from the top. And since I don't suspect that I need those bars all the way out to the extreme left end, I'm going to change the starting location to 10 feet. So they'll run from 10, or mid-span of the 20-foot span, all the way to the right-hand end of the span. And notice that as I make those changes, the graphic changes here on the screen. Let me just also point out that there's a convenience button here, FL, which stands for full length. So with regard to these green bars, if I click that full length button, notice that that revises the starting and ending locations, so it starts at the beginning of the span and ends at the end of the span. And notice too that the green representation of that top bar just changed to run full length of the span. To modify it back to the way that I want it to be, I'll just change the 0 starting location to a 10, and then I may need to just toggle there to register that data and make sure that the program recognizes it. So that's the rebar layout that I'd like to try for span number 1 in our beam. Now we need to remember that we have to come back to span number 2, and we need to change the rebar so that it is representative of what we actually want to build here in span 2. So for span 2, I'll also use 4 number 6 bars located 2 inches up from the bottom of the beam, and I'll let them run for the full length of span 2. And then I'll also indicate that I want to add some top bars, and I'll use the same bar pattern that we used in span 1, 5 number 6 bars located 2 inches from the top, and in this case I'll let those top bars run for the full length of the span. It's a short span, and the point of inflection is over here somewhere, so we'll need them for the majority of the length anyway. So that is a thorough look at how we can use the functions on the beam span data tab to define the size and shape and the reinforcing in each of the spans in our model. The next thing that we'll do is visit the Span Loads tab. The Span Loads tab is used to assign loads to a particular selected span. So we could choose to place loads on either span 1, or in our model we could toggle over and place loads on span 2, and we can provide a whole list of loads on a span by span basis. What we would do to provide loads is we would use the add, copy, or delete functions, and then move over and select a load type. So we can add point loads, we can add uniformly distributed loads, we can add partial length uniformly distributed loads, trapezoidal loads, and even concentrated moments. Let's, for example, just say that we want to provide a single concentrated load, and we'll put it at the 10-foot mark on this 20-foot span, just so we can see how some of the controls work. We already have one line pre-populated for us in this table, so what I'll do is just make sure that that's selected, and then I'll click the point load option, and when I do, notice that that line reflects the fact that I've chosen a point load to define. I might call this something like equipment if there's a meaningful load source that I can add. And then let's just say that I want to provide a magnitude of 0.5 kips dead load, 0.5 kips live load, and that I want that to occur at location 10 feet. So I'll just provide 10 and then toggle up and back down. Now we can see that in this description, we've provided a span 1 point load of 0.5 kips dead, 0.5 kips live at a distance of 10 feet from the left-hand end of that span, and we see exactly the same information echoed in this table. If we wanted to provide additional loads, we could then come over and click the add or copy buttons, and we would get a new line in this table. We could then select the load type that we want to provide, and to define the description and the magnitudes as need be. There are two checkboxes up here that I'll point out now. One of them is whether or not we want to add the beam weight automatically, and the other one is whether or not we want the program to consider unbalanced live load automatically. The beam self-weight is fairly obvious. It uses the unit weight, the section dimensions that we've defined, and it just automatically adds that additional load as a dead load. The automatic unbalanced live load warrants a little bit of consideration because it's important to understand that this can turn into a whole bunch of permutations of calculations that we're asking the machine to run, depending upon the complexity of the loading system, how many different live loads we have defined, and the complexity of the model. How many spans do we have that we need to consider with skip loading? So one thing to consider is that if you want this as a design consideration, but you're still in the process of adding multiple loads, you may choose to leave this deselected for the time being and then just come back and toggle that back on at a later time. Or if you've turned off the auto calculate like we've done in this exercise, then you could safely just toggle on that auto unbalanced live load placement option right now and know that it's selected and it will run when you choose to perform your calculation. Now, I'd just like to reiterate while we're on the span loads tab that if we had any span specific loads that we wanted to have applied to the other span in our model, which currently remains unloaded, then you'd have to come over to span 2 and define those loads here, and that's a function of the fact that we've chosen the option to use the span loads tab, which is span specific loading. I would also comment though that the only caveat to that is these two checkboxes, which are not actually span specific. In other words, when we had the number 1 selected and we chose to auto add the beam weight, that doesn't mean just consider the span weight or the self weight of span 1 but not span 2. This is something, as well as the auto unbalanced live load placement, that is pretty clearly applicable to the entire beam system, not just to a particular span. But they're placed on the span loads tab just for convenience because there's no guarantees that you would necessarily visit the next tab, which is the loads all spans tab, which does apply to loads that pertain to multiple spans. So that's a good segue into our next tab, which will be the loads all spans tab. The Loads All Spans tab, as this node indicates, is used to specify load locations that start at the far left-hand end of the beam system and then progress across the entire beam system as per the specified dimensions. Now that may be easier to just see by way of example. So what I'll do is come down to these options and show that we do have the ability to specify full-length uniform loads, which would by default apply to all spans in this case. But let's say that what we really wanted to do was define a load that started 2 feet in from the left end of this beam system and end 2 feet short of the right hand end of the beam system. This tab is very convenient for doing that kind of thing, because what I could do is define it as having a starting distance of 2 and an ending distance of 20 plus 10 is 30, minus 2 would be 28, so I would just enter 28 feet. I would provide the tributary width and then whatever my magnitude is, and that's a load that would go from 2 feet in to 2 feet short of the right hand end. A little bit quicker and easier than defining that load in 2 separate pieces using the Span Loads tab. Some of the other options that we have include defining trapezoidal loads, where we have a variable, a linear varying magnitude, and we're even given a couple of inputs to specify those, so we can have some pretty complex loading assigned to our beam system given the options that we have. There are also options to specify point loads or concentrated moments, and they can be set up such that they start at a certain distance in from the left-hand end of the beam system and then they occur at so many feet on center thereafter. Or there's also an option to define point loads or concentrated moments such that they occur at each span based on the selected spacing option down here with these buttons. So we can say that each span receives the designated magnitude of point load at its center or at its third points or quarter points. Or we could even come in and say that the specified point loads or concentrated moments are to occur at such and such a distance from the left hand end of the span, and we can define up to 4 of those. So again, quite a bit of flexibility in terms of the way that we can provide loads on all spans of the beam system. What I'll do for our exercise is just simplify things a little bit and come back up to this topmost option and indicate that we want a full-length uniformly distributed load with a magnitude of 1 kip per foot dead load and 1 kip per foot live load. Now I would also point out that here on the Loads All Spans tab we see the same 2 checkboxes for self-weight of the beam as dead load and unbalanced live load placement that we saw when we were back on the Span Loads tab. And just keep in mind that these are just another view of the same 2 controls. So if we make a change to one of these options here on the Loads All Spans tab and then toggle back, we can see that the corresponding change has been made on the Span Loads tab. So don't be confused into thinking that there are 4 different controls here. There are really 2 different views of 2 controls, and the reason for that again is because there's no guarantee that a user would necessarily visit the Span Loads tab if they could accomplish all their loading on the Loads All Spans tab, or vice versa. So as a convenience, we just provided those checkboxes in both locations so that you could use them no matter where you ended up to accomplish your loading. So that's our Loads All Spans tab, and the next tab that we'll take a look at is the Load Combinations tab. The Load Combinations tab contains quite a bit of information and quite a few options, so we'll start over here on the left hand side and just indicate that the tab says LRFD Strength Combinations, and we can see that the combinations that are indicated are at a factored level which is appropriate for concrete. Moving over to the right, notice that there is a Run button here and a series of associated checkboxes. The checkboxes are so that you can selectively indicate which of the load combinations you want to run or which ones you don't want to run. The Run button is to make quick changes to those selections. So when you click the Run button, you can see that you have options to mark all of them for run or clear all so that none run. Sometimes it's easier to clear them all and select the one that you want. There's even an invert selections option, so it'll invert the options that you currently have selected. I'll just leave them all set to run. The next thing that we see is an indication of the load combination set that's currently selected. And associated with that is this button called Change Load Combination Set. Now there's a separate video that covers load combination, the load combination database and how to define load combinations for the database, and a lot of that related information. So I would encourage you to take a look at that video. But for our purposes here in the concrete beam module, what I'd like to show is simply that I can click the Change Load Combination Set button, and I can view a list of the load combination sets that are defined on my machine. And let's say that I want to use IBC 2009 for this analysis and design. I can just click the IBC 2009 load combination set, and that's what is echoed up here, and now I see the load factors that are relevant to IBC 2009 factored level load combinations. Now sometimes there's a need to come in and make a specific change to certain factors for whatever reason, whether it's a project level requirement or a requirement that's specific to a client. And so what we might want to do is come in and use this padlock icon. It's a toggle, so if I click it once I see the unlock view, which means that I could then come in here and I could modify one of these factors, like say the factor on H, the lateral earth pressure, and now I can see that over here in the load combination list it reflects it as being a 1.0 H as opposed to a 1.6. So by way of example, that's how you can make your customized changes, and just rest assured that you're not making a change to the original IBC 2009 load combination set that's safely stored away in a database in your program. All you're doing is making changes to the load factors that will be used to create load combinations for this particular calculation in this particular project file. I'll just come back and reset the view to lock those combinations so that I can't edit them by accident. The next thing that I'll point out is that there's a checkbox labeled Auto Minimize Combinations to Run. What this does is it looks at the load combinations and it looks at the loads that you've defined in your calculation, and it eliminates any load combinations that include snow or wind or seismic loads if none of those loads are actually defined in your model. So it's just an efficient way to eliminate calculation time and results output that would be needless if you don't have those load cases defined in the first place. Coming down the right hand side of the view, we have an option in this particular load combination set. We have an option to specify whether our live load is for an occupancy where the magnitude of live load is less than or equal to 100, in which case the factor on live load would be set to 0.5, or if our occupancy is one that dictates a live load of 100 psf, greater than 100 psf, in which case it would force the load factor to be 1.0. And you can see that change right here in the live load column as I toggle back and forth between those options. Some of the load combination sets incorporate this. There may be some that do not incorporate that convenience, so just be aware that that could be a load combination by load combination basis. Coming down to the bottom, I'll point out that there's an auto reverse seismic factors button, and what this one does is if we select that option, then when we run any load combinations that include seismic, it will automatically incorporate a similar load combination where it incorporates the negative version of that seismic load. So up in here, if I find another one that incorporates seismic, here's one right here. If I have that checkbox checked, then it will create this load combination as well as its counterpart with the -E. And just keep in mind that that -E means that it reverses the direction of application of all loads that you've applied and called seismic load type. Similarly, there's an option to auto-reverse the wind factors because the wind comes and the wind goes. So for your design, it may be appropriate to choose the option to automatically reverse those wind factors so that it looks at both the positive loads as you've defined them, and then it reverses them with a negative sign and looks at the effect of a reversal. And then the last thing that we need to look at here on the Load Combinations tab is this button called Use Additional SDS Factors per the reference section of ASCE 7. So again, this relates to seismic loads, and if you enter a value in here, what this does is it incorporates that small additional amount of dead load that the code says we need to consider due to vertical accelerations. You won't see that factor change in this view, but what you will see on the output where you see load combinations listed is that you'll see the proper multiplication of the factors, including this SDS value, multiplied out and added to the factor that we've specified for dead load, so that you'll have an effective factor that'll be somewhat higher than what you see here on the Load Combinations tab. Okay, so that's a complete look at everything that we have available to us here on the Load Combinations tab, and that also completes our view of everything that's in the data panel up here on the top. So the next thing that we'll do is move down to the results panel, and we'll start by looking at the different options that are associated with the Calculations tab, where the first one will be the Summary Results tab. Now, the first thing that I'd like to point out here on the Summary Results tab is that our status bar is reminding us that a recalculation is needed, and that relates back up to these settings here where we deselected the Auto Calculate option during the modeling process to save the time associated with recalculating after each modeling step. So what we might want to do at this point is just click the Calculate button and let the machine run through all of our defined load combinations so that we can see accurate results in the Summary Results tab. And we might also choose to just select the Auto Calculate option at this point so that any subsequent changes would automatically trigger a recalculation. We don't expect to be making many modeling changes at this point, so we're probably safe to do that. Now back down to the Summary Results tab, we start off with a maximum bending stress ratio. We can see an indication of the section that's used. It just says typical section here, but this relates back to our beam span data tab where we defined an 18-inch deep, 10-inch wide reinforced concrete section of the rectangular shape. Continuing down, we can see the factored applied moment, and we can see the nominal strength of the section. And then we see an indication of a load combination. And this load combination is the controlling load combination. In other words, this is the one that produces this maximum bending stress ratio. It so happens that it produces that ratio in this span, span number 1, at this location, 8.381 feet from the left-hand end of span 1. But coming back to this load combination, I'd just like to point out this nomenclature that's used to define the live load that's used in this particular load combination. We've used the option to skip load the live load on this multi-span beam, and so this is indicating that for this particular run it's the one that uses live load that's applied to the left span, but it skips the live load on the right span. So the L in parentheses indicates the loaded span, and the star indicates the unloaded span in our two-span beam. Now, if we had multiple spans, more than 2, we would see more L's and or more asterisks to indicate exactly which spans have been loaded and which spans have been skipped. Continuing down, we have a report of the minimum deflection ratios, and in this category, the first thing that we see is a report of the live load deflections. So we see them broken down into the maximum downward deflections and their associated deflection ratios, and the maximum upward live load deflections and their associated ratio. And then the last section of deflections is for total deflections, again broken up into a downward and an upward component, reporting the deflections and the resulting ratios. Moving over to the right, we have a category called extreme reactions, indicated to be reported in on the basis of service loads and in units of kips. And these are broken out on a support by support basis. So for our 2-span beam, we have 3 supports. So we can see the dead load reaction and the live load extreme reaction that occur at each of the 3 supports. And in our beam, we don't have indications of reactions for the other load cases because we've only applied dead load and live load to the model. So that's a full look at the summary results tab. The next thing that we'll do is move over to the maximum combinations tab. As we move over to the maximum combinations tab, we can see a report of each of the loading conditions or load combinations that has been run. And note that if we expand this a little bit so that we can see more of the text here, some of these load combinations actually indicate that skip loading condition. So we need to pay attention to that and expand the width of this column enough to be able to see exactly what's actually being run here. Now for each of those load combinations that's run, we see a report of the length of the beam segment for span 1 and for span 2. We see the extreme moment at the factored level that was found to exist on that span, the nominal moment capacity of that span, and then the stress ratio for that span. So that's the maximum combinations tab. Next we'll move over to the moment, shear, and deflection summary tab, where we can see that we have a variety of sub-tabs to view. We'll start off with the LRFD strength stress combinations tab. Here we can drill into any load combination of interest, and for each of the spans in the model we can see a report at incremental slices along the length of the beam, the factored shear, the factored moment, the nominal moment capacity, and then we see a report of the status of the flexural reinforcing area that we've provided. First we compare it to the minimum allowable amount of steel, and then we compare it to the maximum amount of allowable steel. Next we'll move over to the service load deflections tab, and here on a load combination by load combination basis we can see an indication, again at small incremental slices all along the length of the beam, an indication of the deflection that occurs at that particular slice. There's a column for the ratio, the deflection ratio, and then we report the effective moment of inertia that's used to calculate that deflection. Continuing over to the cross-section values tab, this tab looks along the length of the beam and identifies all of the unique reinforcing conditions that occur along the full length of the member. We have a 2-span beam here, but we end up with 3 uniquely reinforced sections to consider because our span number 1 has a rebar cutoff that creates a condition where we have bottom only reinforcing, and then another condition where we have bottom and top reinforcing. So this is just reporting the nominal moment capacity when the bottom is in tension and the nominal moment capacity when the top is in tension for each of those different sections. Notice that when the top is in tension, section number 1 has an extremely low capacity for moment because it has no rebar in the top. Then it goes on to report the gross moment of inertia, I cracked when the bottom is in tension, I cracked when the top is in tension, and then it reports the actual steel area provided at the top and at the bottom. The next tab is called Design Shear. This tab is actually reporting an envelope of design shear conditions at incremental slices all along the length of the beam. It reports the load combination that controls the shear design for the named location. It provides us with the D value that's used in the shear design. Then we see an indication of the actual shear at the factored level that's applied to that section at that location. We see the factored moment that occurs at that location so that we can calculate dVu over mu. Ultimately, we see the shear capacity of the concrete and a comparison of that concrete shear strength to the factored shear. From that, we can determine what's required for shear strength of any steel reinforcing. Then we can sum those two to come up with our total shear capacity for the section. And if I scroll over to the right, we can see that we have what's referred to as the code required spacing. And at times this will come out to be something that's not a nice uniform even number of inches. So then what we do in this last column called suggested spacing is we round down the spacing that's reported in the code required spacing column to something that's more conducive to concrete construction and indicate a slightly tighter spacing that might be useful on the drawings. So that is a look at all of the sub-tabs that occur in the moment shear deflection summary tab. The last tab here in the results section that we'll look at pertaining to the calculations section is called support reactions. On the support reactions tab, we can see a variety of load combinations that are hard-coded into the program. Notice that these are not the load combinations that you've specified, but instead are an attempt to try to simplify the results into some meaningful values that you can use to pull off reactions on the basis of dead load, and in our model, since we have only live load defined, we'll see live load only. That's skip loaded according to the alternate spans to try to maximize the various support reactions, and then we'll see some combinations thereof, including both dead load and live load skipped as well. So for any load combination of interest, we can just expand the results and come right in and take a look at support reaction values for any support of interest. So that's a thorough look at everything that we have to view on the calculations tab down here in the results pane. So the next thing that we'll do is take a look at the sketch tab. The sketch tab presents a graphical depiction of our model. So here we can see a 2-span beam with pinned supports. The section size is indicated as we defined it. Span lengths are reported. The loads that we've applied are shown graphically and indicated numerically. And then what can be very helpful here on the sketch tab is we get a nice view of the reinforcing as it's been defined. So we can clearly see that we have a top rebar cutoff at the midspan location of span number 1. And we can see that our bottom rebar was run continuously from end to end of the overall beam. So that can help in terms of visualizing where your rebar is and where the different design sections or segments will be generated on that cross sections tab. So that's the sketch tab. The last thing that we need to do is cover the diagram tab. The diagram tab is used to display moment, shear, and deflection diagrams for your beam. We can simplify things just a little bit by deselecting the option to display all combinations, and then once we do that, we can come over to the display load combination drop down list box, and we can select for instance one that includes live load on the left span, the long span, and look at the moment diagram for that particular loading condition. If we wanted a little bit more detail, we can actually hover over this icon and get a pop-up enlarged view at a little bit greater scale. If we wanted to take a look at shear diagrams, we can click the shear button, and again we're looking at the shear diagram for the entire length of our two-span beam for the indicated load combination. And then if we wanted to look at deflections, we can click the deflection button and we can see a graph of the deflections for this particular loading combination. Again, we always have the option to display all combinations so we can get a sense for what controls based on the color and the code reported down below, and then we can drill into a particular loading condition of interest. The other thing that I would point out when you're looking at the diagrams is that we have a dedicated amount of vertical scale space that we can use to display these diagrams. So a lot of times when we look at different diagrams from different loading conditions, they'll appear graphically to be the same scale vertically, but what we have to be cautious of is the numerical values that are indicated over here, which actually establish the true meaning to the vertical scale so that we can interpret things properly. So the message there is just pay attention to the vertical scale and understand what this distance actually represents on the graph. Okay, so that is a look at the diagram tab and what we can do with it. The last thing that I'd like to do is just remind you that you have some controls up here to print your reports or view your reports. There's an icon that you can use to establish exactly what items will be included in a report that you either print or save as a PDF, so you have some control over the content of your reports. You can preview your reports, and then you can choose to either print hard copy, or we've incorporated the function to print directly to PDF as well. So that sort of rounds out the output in terms of what you can view on the screen and what you can print and what you can save for your reports. So that's a thorough look at the concrete beam module. I hope that the video has been helpful, and I would encourage you to take a look at some of the other related videos, which would be beam videos of other materials, and look for a concrete column module video as well. Thanks very much. Take care and have a great day.